My pleasure to welcome Dr. Rafael de Oliveira. Dr. de Oliveira did his bachelor's, master's, and PhD in 2007, 2010, and 2014 at Unesp Presidente Prudente. He spent, as we were chit-chatting a little bit ago, he spent a few months or a semester at the University of Bangor in Wales, in UK, and he did a sandwich in Modena, in Italy. He did then his postdoc. He did one postdoc from 2014 to 2018 at CNPEM in Campinas, and another postdoc from 2018 to 2020 at Strasbourg University in France. And since 2020, he is at LNNano at CNPEM Campinas, and currently he's the boss of the nano and micro fabrication division at LNNano CNPEM. We saw that he was called to take care of a fire some minutes ago, so he did that and he came back to talk to us. So today he solution-gated transistors, a versatile platform to electrically characterize thin films of molecular semiconductors to the materials and to develop sensors and biosensors. So Dr. de Oliveira, it is a pleasure to have you here. Thank you very much for accepting the invitation, and the microphone is yours.
Thank you very much, George, and I'd like to thank you and Professor Hiroki and all the organizers for the opportunity to talk here today. How much time do I have?
From between 50 minutes and 1 hour.
Okay, so please interrupt me if I talk too much, okay?
Okay.
So it's once again, it's a big pleasure to talk to you guys today. Thank you very much for this great opportunity. As Professor George said, I'm currently at the Brazilian Center for Research in Energy and Materials, CNPEM, at the Brazilian Nanotechnology National Lab, LNNano, in Campinas, São Paulo. This is the view of our campus. Here we have the city of Campinas, and our institution is a national lab, so it's an open facility coordinated by the Ministry of Science here in Brazil. The campus has 4 national labs, so we have our former synchrotron national laboratory, nowadays called Sirius, in this big facility that looks like as a football stadium. We have the LNBR, which is a national lab in charge of doing research in biorenewable energy. We have the LNBO, which is the laboratory in charge of researching bioscience. And we are here, then LNNano, the Nanotech lab. I'm currently the head of the nano and microfabrication division at LNNano. So we have in our lab 4 strategical scientific divisions. One is our division, is the nano and microfabrication. We have also a scientific division for researching synthesis of nanomaterials, the characterization of nanomaterials, and nanotoxicology. At our facilities in the nano and microfabrication division, we have a couple of clean rooms for micro and nano fabrication. This nanofabrication facility is brand new. It will be a true open facility by the beginning of the next year, where we produce several processes, such as maskless photolithography, several thin film deposition methods like PVD, ALD, e-beam, jet printing, etc. We have also labs dedicated to the electrical measurements of devices, because electronic devices, electrical devices are our main interests here for applications in healthcare, environmental care, energy, etc., and also electrochemistry. Today, I'm going to talk about solution-gated transistors, which is a kind of device that I've been working for a quite long time. For those not introduced in the topic, I'll give you a brief overview. Then I'd like to exemplify the use of solution-gated transistors or liquid-gate transistors or electrolyte-gated transistors, as the literature refers to, by using this kind of device architecture to study the electrical properties, some of the electrical properties of molecular semiconductors. I will exemplify these with the copper phthalocyanine organic semiconductor. I'll show you one or two examples on how this kind of device can be used for chemical sensing and biosensing. And I'll speak a little bit about their use also for the electrical characterization and development of application using two-dimensional materials, more specifically reduced graphene oxide and molybdenum disulfide. So an overview on the topic. So our audience here, I imagine, is quite broad and versatile. So some of you may know the structure of a thin film transistor. You know? So a thin film transistor is a three-terminal device where you have a semiconducting thin film that acts as active material. In other words, you can control the electrical current that flows from this source and drain electrode through the semiconductor film by using a control gauge by applying a given voltage. In this kind of device, it's important to mention that one of the important interfaces is the semiconductor dielectric interface or insulator interface, where you have the accumulation of charges in the channel. In this kind of device, you have as insulator or dielectric, typically a thin film. And applications are mostly in electronic circuits. You know? So, for example, by applying a negative gate potential, you induce accumulation of charge carriers. For example, p-type carriers in the channel, then you can control the current that flows in the semiconductor. This is the typical band diagram for a p-type semiconductor in a metal insulator semiconductor structure. So by applying, for example, negative gate voltage, you induce holes in this interface. So let's do together here an exercise to introduce the other topic that I want to talk about, which are the solution-gated transistors. So by applying the gate voltage, for example, negative voltage, we form a capacitor-like structure in our transistor, which has a specific capacitance given by this equation, where kappa is the dielectric constant of the insulator, epsilon 0 is the vacuum permittivity, and D is the distance between the plates. Typically for electronic circuits, we have thin films of silicon dioxide as insulator, with thickness, for example, in the range of 200 nanometers. By doing a simple math, we arrive here that typically these kind of thin film transistors, in what I called here solid-state thin film transistors, may have capacitance in the order of tens of nanofarads per centimeter squared. So this means that when we operate a thin film transistor like this, we measure the current that flows through the semiconductor via source and drain electrodes, here shown in black for the absolute for the current values, and in blue for the current square root. And then we have when the gate voltage is high, negatively high, we induce larger amounts of current in the channel. Okay, I'd like to bring your attention here that in this kind of devices, we have typically voltages of tens of volts. Okay, this is because of this small gate capacitance. And we can produce thin film transistors in different architectures. So here you have 4 different architectures that are possible. For example, this one that I just showed you, it's a bottom gate, top contact architecture, but we can also have a bottom gate, bottom contact architecture. Or we can turn it upside down and have the contacts in the bottom, the semiconductor film, the gate dielectric, and gate on the top, and then even a top gate, top contact architecture. So this is the one we just discussed. We could have also this one. They are quite similar, of course. Each of these architectures, they have pros and cons. But I'd like to bring your attention to this one, which is our starting point for discussing the liquid gate transistors or solid gated transistors. That means that we can take this transistor architecture and substitute and replace the gate dielectric film by an electrolyte. And here's our device. So we have Again, a solution-gated transistor is a three-terminal device like the solid-state thin-film transistor, where we have source, drain, and gate electrode, and the semiconductor is separated from the gate electrode by an electrolyte. And what happens by doing this? When you polarize the device, for example, by applying, again, a negative gate voltage, you induce the ions in the electrolyte to migrate to both interfaces. So in this case, cations will accumulate at the interface with the gate electrode, while anions will accumulate in the interface of the semiconductor. And what happens in this region that you form what the electrochemists call the electrical double layer, which means that you have a charged surface that solvated ions in the electrolyte will accumulate at very short distance from this surface, distance that range from 1 to 10 angstroms, more or less. So you can operate these devices, these transistors, by using an electrolyte at the interface with the semiconductor. And again, the semiconductor is the active part of the device, and you can control the accumulation of carriers in the semiconductor by the gate voltage. But applications are obviously different from the thin film solid-state transistors. Here we use this kind of device for bioelectronics. This is because it combines both electronic phenomena like charge conduction with ionic phenomena, and ions are the main carriers in biological processes. And this is our band diagram for this kind of transistor. So you have the gate voltage. At this interface with the electrolyte, you form the electrical double layer. At the interface of the electrolyte with the semiconductor, from another electrical double layer that will induce, for example, in this case, accumulation of holes in the channel, injected, for example, from the source. And so we can imagine that if you compare the two architectures, so solid-state thin-film transistors, solution-gated thin-film transistors, to induce the very same amount of charge in the channel, there are important implications if you use a thin film insulator or an electrolyte. So this means that by using the solution-gated transistors, where the capacitance is higher, much higher, orders of magnitude higher than in a solid-state analog, means that you increase the capacitance, and obviously to induce the same amount of charge, we use much less voltage. This means that these devices, they operate at voltages below 1 volt, which is very appealing for sensing and biosensing, for example. Here we have two possibilities of operation for solution-gated transistors. So we have a possibility that I call here field effect transistor, field effect solution-gated transistor, where the semiconductor film is non-permeable to solution ions. This means that you have a substrate, the pair of source and drain electrodes, your semiconductor film, you place a drop of water or salt electrolyte on top, and you immerse the gate electrode. For example, you can use a metal wire here. Then by applying a given voltage to this gate electrode, since the semiconductor here is non-permeable to ions, you will form the electrical double layer at the gate interface and electrical double layer at the semiconductor interface. And these ions will induce carriers in the semiconductor film. In this case, you switch your transistor from on to off, from off to on. But you may also experience in the literature several examples where there might be some permeability of ions into the semiconductor film. And when this happens, this of course depends on the type of semiconductor film you have, its chemical structure. So you may have ions that they enter in the semiconductor film to balance the carriers within it. So in this case, we call this kind of operations electrochemical transistor. And to characterize this kind of device, well, for the field effect transistor operation, you use the same physics you do for a solid state device. So here I have a picture of a device with the geometrical parameters like channel length, channel width. The type of characterization, electrocharacterization you do is you measure the source and drain current while applying increasing the source and drain voltage for different gate voltages. you will have a linear regime of current where the current depends linearly with the source and drain voltage. You may also you also have the saturation regime where the current no longer depends on the drain source voltage, but on the square of the gate voltage. You can calculate the square root of the current, and by doing that, you plot it against the versus your gate voltage, and where you have the transistor here showing an off state, and it switches on, so the current increases. The intercept of this current with the x-axis can be used to determine a parameter called threshold voltage, which is the voltage when the transistor switches on, and the slope can be used to calculate the field effect carrier mobility. So when the transistor field effect operates in field effect mode, so you can use the same physics to characterize the device, even if you are using a solution-gated transistor. But when the transistor is in electrochemical mode, means that you can operate in two ways. So what is called depletion mode and accumulation mode. Depletion mode means that here we have the band diagrams for both modes. You form electrical double layer at the gate interface. You form electrical double, and your ions will migrate towards the inner part of the film, and you no longer can inject carriers in the semiconductor. This means that when you increase the gate voltage, you decrease the conductance in the channel. Or you can do depending on the material, you can have an accumulation mode, which means that by increasing the gate voltage, the current increases because you dope your semiconductor with these electrolyte ions. I want to bring your attention to the current equation, where it contains here the film thickness, which means that if your current depends on the film thickness, you have an electrochemical operation mode. Here there are two pictures that show how before polarization of the gate and after a positive polarization of the gate, that shows that anions accumulate at the gate interface, while cations, they enter in the semiconductor film and may dope or de-dope it, depend on the material. And to illustrate that, I'd like to show you an example with this semiconducting molecule. It is a copper phthalocene, very standard molecule used in different applications, even as a dye for change the color of clothes, for example. And to fabricate devices, we use microfabrication techniques and photolithography. So we can pattern electrodes on the surface of silicon dioxide. We can have the gate, instead of an immersed wire, we can have the gate on the surface, what we call here is a coplanar gate architecture. This is one of the advantages of the solution gate transistor. You can have a coplanar gate instead of having alignment between gate and channel. We can pattern on glass. We can pattern also on plastics such as PET. And this is the standard illustration of how the photolithography process works, where you use light to create a pattern on a given surface using a photoresist. So for our semiconductor molecule, so we start from the pounder. We sublimate the pounder by heating it in a vacuum chamber to form a thin film. Here you have the film in blue of our copper phthalocene molecule deposited onto interdigitated source and drain electrodes. We place a drop of water on top and immerse the gate electrode. Here's a real picture of our device. This is a device that we fabricated and published the data back in 2016. You have here the micromanipulators for the electrocharacterization, the gate, electrode, the source, and drain. And here's the electrocharacterization. So we have the source drain current versus the drain source voltage, where we show that it operates like a regular transistor. I'd like to bring your attention that this device showed a p-type transistor behavior, which means that by increasing the negatively the gate voltage, the current increases. We have some hysteresis here that I will discuss in a while with you. If we plot the current or the square root of the current, you can also see the device switching from off to on. Again, there is some hysteresis. And from the slope of the curve, we can, in fact, extract, well, the threshold voltage, which is around 100 millivolts, the on-off ratio, the current ratio between on state and off state can also be calculated from the curves. And from here, what we can calculate is the product between the carrier mobility and the capacitance. So I cannot extract solely the mobility from this characterization, but I can have these two parameters multiplied together, meaning that the carrier mobility is an important parameter while characterizing semiconductor films. So these devices help us to extract these two parameters together. For this case here, we found this band. With the same device, you can just change a bit the electrical configuration. So you can short circuit source and drain, okay? And use impedance spectroscopy to probe the capacitance at our device interfaces. So here we have a curve, which is the capacitance versus frequency obtained from electrical impedance spectroscopy, that we see that when the electric fields oscillate at very low frequencies, we expect that the electric field oscillates very slowly, so we have enough time to achieve polarization and form the electrical double layers. So what we expect is a plateau here for the capacitance of the electrical double layer. What we saw for this device here was there is we don't reach a plateau, although we observed values that agree with the theory for the electrical double layer around 3 microfarads per centimeter square. And by superimposing a DC bias here, what we see is that there is an increase of capacitance at low frequencies. So by using these values, so now we can calculate and extract the mobility, allowing us to use this type of device for extracting important parameters that characterize the electrical properties of semiconductor thin films, more like organic semiconductor in this case. As I mentioned, so we observe that we do not reach a plateau, and we have also an increase of capacitance by applying a DC bias. This phenomenon was quite curious to us. We also observed that if we measure the current as a function of time, and then we switch on the device is quite slow to switch on and reach a on-state current. And we extract switching times quite high, around 300 milliseconds for the formation of the electrical double layer. These also, how can I say, we also found this a bit suspicious. So, and then what we realized that for cases, by reading the literature, for cases where you have moderate hysteresis that we observed and slow switching times and capacitance changed by that varies with the increase of the DC voltage, we may have some iodoping. However, if we fabricate films with different thicknesses, we observe there is no huge variation of current by increasing the film thicknesses. So it means that we do not have a complete electrochemical operation, but rather a mild interfacial doping. So perhaps this is a hypothesis that we published. We have ion penetration just in the few layers of our film. As I told you also that these devices can be useful for demonstrating proof of concept sensors and biosensors. This means that we can functionalize, we have two interfaces that can be functionalized with chemical receptors or bioreceptors, which is the gate electrolyte interface and the semiconductor electrolyte interface. So here I illustrate, for example, the mobilization of receptors that will interact with a given chemical or biochemical species in solution. This means that, for example, if I functionalize the gate electrode, I will promote some change at the interface capacitance here due to the presence of a bioreceptor or biomolecule at this interface. Physically speaking, what happens is that we change the effective gate potential that controls the channel. And that's what we did for a given biomolecule that we were interested in a few years ago, which is this protein here called glutathione transferase, which is related to Alzheimer's disease and Parkinson's disease and cancer. And this molecule interacts very specifically with this peptide called reduced glutathione. And this peptide has an interesting chemical structure because it has a thiol group here in its structure. This means that we can take advantage of this group to functionalize our gate electrode if we use here, for example, a gold gate wire, and that's what we did. So we use this peptide as a bioreceptor to interact with this protein and detect it in solution. So we use a gold wire as the gate, where we use the peptide as receptor that will interact with our protein, GST. So what we did here, we used the transistor to monitor this biochemical interaction, biospecific interaction. So here we have the transistor current as a function of the gate voltage, where the black curve is our initial transfer curve, so where the gate electrode is not functionalized. And by functionalizing it with the bioreceptor, the current drops significantly because we created a layer of biomolecule here that causes some perturbation to the electrical double layer, reducing the effective gate potential that modulates the channel current. By exposing it to the protein, what we observed is a slight increase of current. That's because this protein is negatively charged in solution, meaning that it induces more p-type carriers in our device. If we take this modified gate electrode with bioreceptor and protein, expose it to a very high concentration of bioreceptors in solution for eluting these, to remove these, so we can reversibly remove the proteins. When we do that, the current goes back to its previous state. And if we remove completely all organic matter on top of the gate electrode, we recover the initial performance. This means that we can reversibly detect biomolecular interactions. And here I show how the current changes at every step of this process of functionalization detection, and also the product carrier mobility times interface capacity. Well, speaking about solution gate transistor in 2D materials, I'd like to show you some results from the time I was at University of Strasbourg in France, which is a CNRS institution. I was at the Institution for Supramolecular Chemistry in Strasbourg, where they are experts on 2D materials and dressing 2D materials with molecules. 2D materials are very interesting materials that are hot topics nowadays, because there are several types of 2D materials presenting different electrical properties. So you can have like the hexagonal boron nitride, which are electrical insulators. There are also semiconductors such as molybdenum disulfide, molybdenum diselenide, tungsten diselenide, have metals, semi-metals, metals, and superconductors. There are more than 150 known 2D materials that occur naturally. I'd like to show this slide, which is many people talk to me. They say, "Well, 2D materials are a great represent a great opportunity for doing interesting science," but it can also be seen as a rat race because since Guy and Novoselov they reported the discovery of graphene and they won the Nobel Prize. The number of publications over the years with graphene in the title increased absurdly, and by last year we had more than 37,000 publications on the topic of graphene. This makes more than 4 papers per hour or 102 papers per day on graphene. So it's difficult to keep up with the graphene literature. Similarly, if we do the same analysis for molybdenum disulfide, which is a very studied material, the numbers are also increasing, and we have now more than half a paper per hour published about this type of material. So it's a great opportunity for doing science, but also difficult to keep up. I'd like to speak about the graphene family, which we use for developing solution gate transistors. So graphene, which is this single atom thick, it's a layer of a carbon atom, a single layer of carbon atoms, which present a very high electron delocalization over the flake. So it's a highly conductive material, but a material that's not easy to process for making devices. So you can use, for example, chemical vapor deposition or exfoliation, like the Scotch tape method that Guy Novoselov used. And these methods they are quite expensive in the case of CVD, or not scalable in the case of mechanical exfoliation. But graphene oxide seems to be very interesting. It's also this monolayer of carbon atoms, but it presents many different types of oxygen defects, oxygen groups, both in the edges of the flake, but also in the basal plane. And because of this, it's very insulating material. Although it's very cheap and easy to process, it can be processed also in aqueous solution. And you can convert the graphene oxide into a more conductive version of it, which is called reduced graphene oxide, by reducing it to eliminate a great part of these oxygen groups. And this can be done via chemical, thermal, electrochemical, electrical methods. So you can combine this easy processability of graphene oxide with the electrical properties of reduced graphene oxide. We fabricate solution gate transistors of reduced graphene oxide on plastic. We started from a gold-coated plastic foil, where we create the electrodes with the assistance of a laser via a laser ablation method. So we remove the gold from the places that we do not want. In this case, we fabricate a Coplanar gate architecture. Its advantages are it's industry scalable, can be customizable with the laser. You can pattern whatever structure you want. It's also fast. It does not involve lithography, the use of clean room, and you can produce several pieces, hundreds of pieces per dollar or per euro. We used an adhesive layer to keep the graphene oxide in place. So we use this polycation. So we immersed our plastic substrate just to the middle, where we cover with this adhesive material, creates a 1 nanometer thick adhesive layer. And then the graphene oxide, we use the commercial graphene oxide. So we cover just the pair of source and drain electrodes. And we reduce it just in the channel region to create reduced graphene oxide just here and not in the other parts of the device. This allows us to have spatial resolution. And in this case here, we reduce the graphene oxide via electrochemical method. So we use a potentiostat, where we have our substrate with source and drain electrodes, the adhesive polymer film, the graphene oxide flakes. We put a drop of water sitting on top of the film. We close the circuit with a gold electrode, and we perform a few scans of cyclic voltammetry to reduce graphene oxide, transforming it into reduced graphene oxide. Again, the advantages are this method is fast, reproducible. In this case, we use water, so it's free of any solvent or aggressive chemicals, so it makes our fabrication environment friendly method. It's non-expensive as well and scalable. Here's a picture of the real device on plastic, and here I show you, you can see the contrast between these two regions, where here we have the interdigitate source and drain electrodes. This region here is the graphene oxide region, and the slightly darker region is the reduced graphene oxide, which has a much lower resistivity than the graphene oxide. And this can be used even on such rough surface such as plastic ablated by a laser. So it means that this kind of film covers even very rough surfaces. I think surfaces, the roughness here is pretty high, like more than 50 nanometers perhaps. And the method is compatible with several different types of substrate, as I told you. So here is a picture of our device under measurement. So we confine the electrolyte using a porous membrane sitting on top of both source and drain and gate. And here's the typical curve of reduced graphene oxide, that it's supposed to be ambipolar. An ambipolar material, meaning that when the gate voltage is negative, we have a conduction via hole, so it's a p-type conduction that reaches a minimum current value and rises up by presenting an n-type conduction. By doing the math, we can extract the charge carrier mobility both for holes and for electrons. So again, how to use this kind of device architecture to measure the electrical properties of thin films, in this case, semi-metal reduced graphene oxide. We use this device also for doing chemical sensing. Here I have a more sophisticated device architecture, but I want to call your attention to these two guys here in the middle, the two transistors. A transistor designed to detect sodium ions, and a transistor designed to detect potassium ions. And by doing that, we functionalize here the source and drain reduced graphene oxide region with chemical receptors. The one for potassium is this macromolecule here called valinomycin, and another one for sodium. And here I will not go into the details, but you can measure the current, the transfer curves of the device, both continuously or as a function of time, and the transistor is sensitive. The functionalized transistor is sensitive to different concentrations of the ions of interest. And we did this because we were interested in developing a wearable sensor for detecting chemical species in the sweat of athletes. And this is what we did within this project called Graphene Flagship. Back in the time that was in Strasbourg, coordinated by my former supervisor, Professor Samui, where we developed a prototype for a chemical sense. Let's see if I can run yes, I can run the video. So we have the electrodes, the flexible electrodes. We have a paper membrane to protect the electrodes and dry the sweat. We developed the electronics. I'll stop here. We can also, I'll skip this data because it's an ongoing project which is confidential, but it's biosensing. So we use the gate to functionalize with biomolecules for performing biosensing. Another interesting story with 2D materials, and by the end of it, I'll show you their use with solution gate or liquid gate transistors. is by using a transition method like cogenase. These are interesting semiconductor materials. Here's a picture of molybdenum disulfide crystal. And this material here, when it's a bulk, in its bulk form, it's a semiconductor with indirect band gap. But when you go down to monolayer, it's a direct band gap semiconductor. So this kind of material became very interesting for optoelectronics. And this class of materials can present different band gap energies. So molybdenum disulfide, molybdenum diselenide, molybdenum telluride. So they are very appealing for optoelectronics, electronics in general. There are several methods of producing 2D materials. Here I have this famous plot from the paper of Konstantin Novozlov in Nature, where he presents different methods and a relationship between the quality of the material that you produce in terms of defects, okay, and the price for mass production. While this method here, the mechanical exfoliation using the Scotch tape, reported by Novozlov and Gein, that ended up in their Nobel Prize, produces very high quality materials of very high quality. It's also it's not cost effective. It's not cheap at all to produce in a large scale. There are several methods that I will not go into the details, but I'd like to bring your attention to the liquid phase exfoliation that allows one to produce inks of 2D materials. So here we have a picture of graphene oxide ink and molybdenum sulfide ink. In this case, we exfoliate the flakes via intercalation of molecules in between them. So, and this way you can produce 2D materials in large quantities. Here, for example, it's a scanning electron microscopy image of molybdenum disulfide film deposited on a given surface and produced via liquid phase exfoliation. And this kind of film has large applicability in electronics, in energy, health care, environmental care, depending on the device that you do with this kind of material. But this kind of material can also present structural defects, and the types of defects one can have is 0D defects, which are vacancies, and these vacancies, they form at very low energies, like around 2 electron volts, for example, for sulfur vacancies in molybdenum disulfide. You can also have linear vacancies or defects, and also what the literature calls 2D defects, when you have folding of the flakes or rippling. Here it's the illustration of types of vacancies one can have, like single sulfur vacancies, double sulfur vacancies, molybdenum vacancies, so on and so forth. And these vacancies, in electronic device, they can act as a charge scattering centers. And during the exfoliation of these materials, for example, during sonication, they are likely to propagate, so you can have several defects per flake spread all over your film. And as I said, the most common is the 0D defect, the vacancies. And when you pile up several flakes like this, the charge transfer becomes compromised, because there always be a energy barrier in between 2 adjacent flakes, meaning that to transport current along these films, the electron will always face an energy barrier. So there is a poor interflake electron connectivity for this kind of sample. So here's what we thought. So how can we improve the electrical performance of solution process 2D materials, especially the metal disulfides? One possibility is what the literature calls defect engineering. So we took our molybdenum sulfide semiconductor, which has sulfur vacancies, and we functionalize it with this molecule called BDT, it's the benzene dithiol. So it's a benzene core, so with a core with delocalized electrons, and 2 thiol groups to not only heal the vacancies by substituting the vacancies with these tile groups, but also bridging two adjacent to close flakes. So what we did was, okay, we prepared our ink, and we demonstrated for different metal disulfide inks, molybdenum disulfide, tungsten disulfide, rhenium disulfide. We deposit on top of interdigitated electrodes, so we have the flakes spread on top of the contacts here for the electrocharacterization. We expose it to the benzene diethyl solution, and after some thermal treatment to evaporate this solvent, we expect that these flakes will be bridged together. Here is the high-angle annular dark field imaging of our films. So this in fact is our film. So you can see here that it has defects over the flake edge. Here's the basal plane of one flake. If we measure the molybdenum distance for our material, we see that it's quite large, the variation. And by comparing with the basal plane of the solution processed material, the basal plane of the molybdenum sulfide produced by mechanical exfoliation, and the basal plane of a material produced by CVD, you see that the molybdenum distance in the basal plane agree for these three. So the values are pretty much similar, but our values are broader. This means that our device is very detective on the edges because it stresses the molybdenum bond nearby by the edges, and you can see clearly here the defects on the edge. Here is the scanning electron microscopy image of what we call film, which are the flakes together but no molecule, and what we call network, which is when the molecules are used to bridge these flakes. So we see no macro or micro differences, nor from AFM, so no big differences. And here we have films that are pretty thick, like around 700 nanometers and pretty rough. So we don't see any difference in this case between films and network. But we do see from X-ray photon electrospectroscopy analysis. Here we have the typical sulfur spectrum for the film, where you have the typical peaks for sulfur, and this broader peak or shoulder here, it accounts for the defects around 161.5 electron volts. And by doing differentialization of VDT, this peak here disappears or reduced significantly. If we do the ratio between the areas of the peaks, we see that there is a decrease of this contribution here from 8% to 5% when we use the molecules. If we do also the ratio between sulfur and metal from the XPS data, we see that there is a slight increase of the ratio between the signal from the two atoms. So from this data here, we can claim there is healing, so substitution, the attachment of the molecules to the sulfur vacancies. But what about the bridging that I talked about? It happens as well. So here we have the surface contact angle of films and networks. For films, the surface is quite hydrophilic, with presenting contact angles around 53 degrees. What we also observe for films, so no molecules involved, is that some flakes, they float in the water drop, meaning that there is some detachment of flakes when you expose this film to water. For networks, so flakes bridged together with the BDT molecules, the contact angle is higher, is around 121. This is because the BDT molecule, the benzene core, is quite hydrophobic, and there is no detachment. So this is an evidence that the molecules are doing their role, though they are bridging flakes together. Here's scanning electron microscopy for films, neat films, and films after washing. You can see that they detach from the surface, and networks after washing. So we don't see clear detachment from the surface for flakes having molecules bridging them together. So here we are, the solution gate transistor or electrolyte gate transistor. So to probe the electrical properties of these films and network, we use this kind of device because it allows us to probe more easily the accumulation of carriers at the interface with the electrolyte than the interface of the silicon dioxide. And what we observed here is that here is the transfer curve of transistor for the two cases. So in black, we have the transistor current for films, while here in red, we have the transistor curve for networks. So there is a clear improvement of the performance by 1 order of magnitude. If we calculate important figure of merit for films and networks, we see that the field effect mobility increases by a factor of one order of magnitude. The on-off ratio increases also by 1 order of magnitude. The threshold voltage remains nearly the same, meaning that there is no doping, there is no charge transfer from molecules to the material, to the molybdenum and the sulfide. And the switching is faster for our devices employing networks. I'm almost done, okay? Just 2 or 3 more slides. But we wanted to understand deeper the charge transport. So we performed charge carrier transport investigation. So here we have films and networks. So for films, we have the current versus here the electric field. And films and networks at room temperature, they present nearly the same current characteristics when using a 2-terminal device. This is because here the transport is dominated by the film contact Schottky barrier. Here we have the typical Schottky plot that we can extract the barrier high. So what we did to circumvent this is we applied the gate voltage to lower the barrier and to probe the bulk transport properties of film and network. And then what we observe is that the networks, they present higher currents than films by applying a significantly high backgate voltage. Meaning that now we are probing the interflake transport for films and networks they have an improved transport. Meaning that our hypothesis of using these molecules, the localized molecules, to improve the interflake transport, these molecules they indeed improves the transport. If we plot a Hennius plot for the current logarithmic as a function of the inverse of temperature, we can extract the activation energy for this transport. And we observe the activation energy is around 500 millielectron volts for films, and it decreases to 300 millielectron volts for networks. Once again, showing that the transfer becomes facilitated. If we use molecules that they have one tile only, and the localized core, so they are able to heal the vacancies, but not to bridge the flakes, what we observe is activation energy is quite similar to the situation of where we do not have molecules. So this slight decrease is because we are healing defects that are scatter centers of carriers, but we do not bridge in this case using this molecule. So there is no significant decrease of activation energy and facilitation of transport. Last but not least, so we asked ourselves, so is the sulfur vacant style the actual functionalization mechanism responsible for what we observed? And is the linker score relevant? So we performed two experiments. So here we have two transistor curves. One where we functionalize the molybdenum sulfide film with this molecule that has a delocalized core, electron delocalized core, but two amine groups. So they are not able to heal the sulfur vacancies. And what we observe is the performance is nearly the same. No current increase. So this molecule cannot do the job of the BDT. And molecules where have this PDP that have the two tiles, but non-delocalized core, meaning that here you have alkyl chain. And what we see is there is an increase of performance when we use this kind of molecule. So this molecule promotes the bridge, and this results in increase of current. And why I'm telling you it promotes the bridge? If we do the wetting experiment that I showed you a few slides back, there is no detachment of flakes, meaning that this molecule is able to put flakes together, to bridge flakes together. But the performance increases just by a factor of 2 or 3, and not 1 order of magnitude as we saw for the PDT. So not only we have to heal the vacancies, not only we have to bridge the flakes, but the core of the molecule we use is also important. So by this, I just showed you how solution-gated transistors can be used to electrically characterize films of molecular semiconductors, films of 2D materials, and to develop chemical sensors and biosensors. So if you want to electrically characterize a semiconductor, develop a sensor or biosensor. Sorry for the mistake in here. This is in Portuguese, biosensor. Electrolyte gate transistor or solution gate transistor may be an interesting tool, an interesting device. Thank you very much for your attention.
Thank you very much, Rafael, for the very nice talk. So the talk is open for questions. So let's see if I have a couple of questions here. I recall a long time ago, the first time I saw this electrolyte gating stuff was maybe 10 years ago. Does that make sense? Would be 10 years ago.
It does.
Yeah.
It started by 2010.
Okay.
Not actually the concept, but they used to study the characteristics of organic semiconductors. This started 10 years ago.
Okay. I recall the context I saw that was gating of superconducting high TC films, because apparently from what you showed there, you need much lower voltages. So if you apply a higher voltage, I assume that you can, well, this gating was to change the Fermi energy, to bring the Fermi energy to deplete or to dope with electrons or to dope with holes to move the Fermi energy. But I didn't follow. That was just something I saw at the time. I thought was interesting, but it has evolved tremendously. It has become a whole field on itself, and very interesting.
What I see from the recent literature is that this type of device became very, very appealing for what is called bioelectronics.
Okay.
Here, well, unfortunately, I have not developed yet any application by using this device to interface the living matter. So, like for example, cells. But colleagues all over the globe have been doing these kind of things. You can stimulate cells, for example, neurons, to respond, to communicate with each other by using the transistor to stimulate them. So this is because you have a flow of ions at the interface cell and semiconductor. So the most appealing characteristics of this device, it combines ionic currents and electronic currents. So you can do what the experts, they say, people in the literature, they say that it's ideal for bioelectronics because biological matter use ions for processes. So it's the main charge involved. So, and speaking about you said about the voltage, so you have to use voltages that are lower than the potential for the water electrolysis.
Yeah, I was going to ask that. What is the limit of the voltage that you can apply?
Yes, depend the type of medium that you use. For example, aqueous solution, you have to play with voltage below 1 volt, which is sufficient to gate the transistor to control. But in case you have, for example, this case of the molybdenum disulfide, because of the Schottky barrier, injection is not quite easy. So the currents are very slow. We use the ionic liquid, so you can use slightly higher potentials around 2.3 or 4 volts. Okay.
Yeah, that was one question. I was very curious about the, if I understood correctly, if you could go back to the slide for the CUPC. I understand that the CUPC was the active channel, right? In this.
Yes.
So what is this? Is that is a thin film, right?
Thin film.
Is it a crystal or a polycrystal?
Polycrystal.
A monocrystal is a polycrystal. Yeah, that's what I thought, because to make a monocrystal, that is impossible.
When you sublimate the molecule, it starts, at least that's what the literature says about this molecule on top of gold, polycrystalline gold, because the electrodes are also polycrystalline gold.
Okay.
So with these molecules deposit at room temperature on top of polycrystalline gold, and also the glass here slide, the very first molecular layer is made of molecules that lie onto the surface. Then, as you increase thickness to 2 molecular layers and more, because actually what here we produce quite thick films if we compare to the molecule structure itself, 50 nanometer thick. It starts to arrange, the molecules start to arrange themselves in small domains of molecules, not lying, not upstanding, but something in between.
Okay. So it's highly anisotropic.
Yes.
Okay. So that was one. And well, you answered that. The molybdenum disulfide is also the active channel, because I was surprised at the beginning. I said, well, how is that going to work? But you showed that it works, right?
Yes.
So that's really very interesting.
What I call the active material is the material that goes in the channel. I don't use the word semiconductor because I presented here different materials. For example, molybdenum disulfide can be called semiconductor, but reduced graphene oxide is a semi-metal. So I call this active material or channel material or active channel. Okay.
No, I understand. Yeah. So let me see here.
I don't know if my microphone is working.
Yes.
Yeah, Roberto, Hiroki, please.
Yeah. No, it's working. So Rafael, thank you for your presentation. Very nice. It's working.
Yes, I can hear you.
Okay. So in your last presentation, your last slide, you presented some MEOS2.
I don't hear you any longer.
Hiroki, I think, where is he? Is he still here? Your microphone is off. Let me send him a message. He's back.
Okay. So you presented the Ame molybdenum sulfide, two layers and interconnected by molecules. So you say that the transmission increased, the current increase due to the interconnection between the layers through the molecules. Is that correct?
Yes.
Correct. Yes. So I wonder, it's in this case it's necessary to connect the vacancies to healing the vacancies for both sides of MEOS2. Yes.
Yes.
Yeah.
Each flake has several defects in the edge.
In the edge.
Yes. Let me go back to the presentation. Maybe I went.
So the vacancies are more at the edge, not in the inner sides.
No, in the basal plate.
Yeah.
Okay. Do you see my screen?
Yeah.
Okay, so let's talk about the figures on the left. Here we have the data from high-angle annular dark field imaging
understood.
for the solution processed material of ours. This is its basal plane. This is its edge. Here there are no defects. The defects are here on the edge.
At the edge. Yeah.
And the molecules, they functionalize these defects here because there are no defects.
So okay. So I was thinking that the connection was in the not the edge but the basal plane. So, but not so, because I wonder if it's possible to increase the distance between planes, like a polarization of the systems by incorporation of molecules with larger length, so you can increase the vertical distance between the layers. But it does not occur because the connection occurs at the edge sides. Yes.
Yes.
Yeah.
Our hypothesis is so you have to remember one thing. This is not a monolayer device. This is a bunch of flakes all together on top of each other. It's a film made of several flakes with a total thickness of 700 nanometers. So it's very chaotic. It's several flakes on top of each other. So there will be several discontinuities from flake to flake to bridge along the whole channel. So from source to drain, the material in between, there will be several edges. So here, when we use the molecules, what we are improving is the interflake transport. So how the charge flows from one flake to its neighboring flake.
Okay. Yeah, understood. Thank you.
I have a question. Did you? Now I am realizing I was thrown off by your cartoon, because your cartoon showed one molecule here, another molecule there, but from the number of edges of edge defects that you have, that you clearly showed there, you need several, or let's say, the more molecules you have bridging, the better should be the transport. Did you do a study of increasing the concentration of molecules slowly, or better, doing different solutions with higher and higher concentration of molecules to see, let's say, if you have a very small concentration of molecules, you should have a poor result. There is an optimum concentration that is commensurate with the amount of defects you have. That would be my question.
Yes. We used 50 millimolar of solution of concentration for this molecule.
Okay.
And then we measured the transistor performance. Then we exposed the films again with the solution again, and nothing changed. Meaning that 50 millimolar was sufficient to bridge all possible flakes to heal all possible vacancies. Of course, you're not healing all the vacancies, you're not bridging all the flakes. But if you consider some diffusion of these molecules, some percolation of these molecules through the film, 50 millimolar is sufficient to observe the performance increase we had. So, but we didn't study variations of the concentration. There was no time for that, unfortunately.
Okay.
I don't know if the guys are doing this back in Strasbourg, because this is actually the result from the thesis of a student called Stefano Ippolito. I have to mention his name here. He's a student from Professor Paulo Samori back in Strasbourg that I had the pleasure to follow him day to day in the lab and guide and suggest experiments to do, analyze the data, and write the paper together. So unless the student is doing this kind of study that I'm not aware of, because I came back to Brazil, we did not investigate that.
Okay. So that also leads me to think that if you the less vacancies you have, the worse should be your result, right? Because you're gonna have less bridging, and the transport will be less, I assume, right?
Yes, but by default, let's say, these materials will be very defective.
Okay, there is no way of producing.
The way that you produce it is the way that you produce it.
Okay, there is no way of controlling and saying, let's make a better, less vacancies, and then look again, and then you see that the result is worse. Well, it's good to have a bunch of vacancies, because then you're going to have more bridging and the result's going to be better.
This topic called defect engineering of 2D materials is becoming very, very popular.
Okay.
So researchers, they either heal defects or they create defects in these materials to study their properties. For example, defects may be problematic in this case for electronics because they are scattering centers for the transport, but they are also catalytic centers for electrochemistry. So defects may be good. They may be good.
Okay. You understand that theorists, they believe that there is a button for everything, right? That there is a dial that you can control everything.
No.
Because there is for us, you just change the numbers, and but we understand that in the lab is different.
In the lab, it's a completely different world.
It's a completely different world. Sometimes I wonder how is it possible that our very rough and incomplete models manage to more or less explain stuff that happens in the lab, because we cannot, unless, well, I'm speaking for myself. I do low energy models. Hiroki does the real stuff. The FT is more ab initio. So yeah. I thought you were going to comment on that. There is a difference in of an order of magnitude in precision, obviously, on what the FT can do and the kind of models that we can work with, because we do mostly strongly correlated, where a DFT doesn't work. So you have to work with models anyway. But so I don't see any questions written. So if there are, Edson Werneck, who opened the virtual room for us, you talked to him at the beginning. He asked me to apologize. He had an emergency,
No problem.
and he had to leave. But he said that what he saw, he liked it very much, and very, very interesting results. And it's very nice to know that the national labs are doing high quality research. That's what it's very exciting. Very exciting.
Well, just to point out once again, so this molybdenum disulfide work and the reduced graphene oxide work was done back in Strasbourg when I was hired there. But liquid gate transistors, solution gate transistors, is something that I've been doing since 2014. So it's something that I like quite a lot. And here my research in the national lab will focus more on bioelectronics.
Okay. Which is very, very interesting. Very interesting.
I hope to have some nice results to show you perhaps next year.
Well, I was going to say that we're gonna be contacting you again to talk to us again in the next semesters.
Good. Thank you very much again.
Okay, so thank you very much for the nice presentation. And I will be writing an email to you soon to ask for the slides if there is no problem. Can you provide the slides to us to post together with the video?
Well, actually, yes, this is something we have to discuss because I ended up showing some content here that is quite sensitive because we have patents under.
Okay. If you can remove as much as you need, and then Okay, no problem. Thank you so much. I will be writing you an email in the next day or so.
Okay, good. Thank you.
Okay, thank you very much again, and we will see each other again for sure.
Sure. My pleasure.
Okay.
Bye-bye.
Bye-bye.